Okay, hi everyone. So we've got two more lessons on content on fields. We've got today's stuff on particle accelerators, and then the next lesson is going to be sort of a summary of stuff that we've done. Not quite revision, there'll still be new material for that, but you'll see that's about next lesson. It's still new stuff. So just keep in mind that because we're nearing the end of this area of study, you are going to have a SAC coming out. You're in fact going to have two SACs. One of them is going to be that you get a particular topic related to fields. You need to research that. It'll be something you haven't looked at before, but it's going to involve the concepts that we've covered when we've done stuff on fields. And so you'll just be given a topic in 2 lessons to research it and write about it. I think you write a maximum of something like 2 pages. You just need to think about, what the thing that you're investigating is and what the physics behind it are. So that's going to be the first SAC. You're going to be doing that through Teams. Just during allocated class time, you'll be given the topic, you research it, you submit your work that you've done by the end of the lesson. And then the second lesson, the final lesson, you pick that up at the start and then finish it off and then submit it by the end of that second lesson. So keep in mind that that's coming up. There's this lesson, the next one, and then rather than do revision, I'm just going to launch straight into that SAC. So when we do that SAC, I might give you a bit of notice about what the topic is, maybe, but we won't be doing revision before that. When we will be doing revision is before the second SAC. That's going to be a test SAC, a pretty short one, but it's going to give a chance to assess on some of the stuff that the first SAC didn't quite assess on. So we'll do the written SAC through Teams, 2 lessons on that, 1 lesson on revision, and then you're going to have a test SAC, which I think the best way to do it is for you to come into the school and actually do it under test conditions in here. It's going to be much easier than trying to type things through whatever computer document you want to use or trying to write it down and then scan it. So I'm just going to be contacting home over the next couple of weeks, making sure that people feel comfortable coming into school. It's a small class, so we probably shouldn't have any issues running it here. Anyway, this lesson is on particle accelerators. Here I've got a photo of the Australian synchrotron over near Monash. It's just a particle accelerator, one that we have in Australia. And synchrotrons are going to be our main focus today. I know it says particle accelerators. That's the name of the chapter, but the main focus here is on a particular type of particle accelerator called a synchrotron. We're going to be looking at how those work and what different parts they have. So what we're looking at is going to tie in with the stuff on electric and magnetic fields and forces that we've been doing up until now. So here I've got a schematic of a synchrotron. You can see a few parts to it. The way it works is that it starts in what we call an electron gun in the middle, goes through a LINAC, which stands for a linear accelerator. So the electrons are fired from the electron gun, go to the linear accelerator. A linear accelerator uses strong electric fields to accelerate the electrons to high speeds. They go to a booster ring, which further speeds up the electrons, and then the electrons go out here into what we call the storage ring. And in the storage ring, we've got magnets that cause them to bend and change direction. The electrons are just stored in the storage ring until they need to be used. When they do need to be used, the idea is that when electrons change direction, they can give off light. They can give off very strong light across a very broad spectrum. So that's why synchrotrons are useful, because they can produce high intensity light that you can't get from other places. And not only that, they can produce it across a very wide range of light. So if you're doing an experiment and you need strong light, and you need it at a particular frequency or within a particular range, then the synchrotron can provide that. That's basically what it does. Speeds up electrons. It's not a particle collider. You get those, but that's not what a synchrotron is. All a synchrotron is basically a very strong and expensive light source. It gets the electrons to produce light, and then you can get the light being given off down to the side here, where people are set up doing an experiment. They can get the light from these electrons in the storage ring. They use that light for whatever they might be setting up an experiment about. So that's basically the gist. Electrons are fired, accelerated even more, and then kept in the storage ring at high speeds until they're needed, in which case the light that they need is produced from the electrons, goes out to the side here and is used for an experiment. So that's what a synchrotron does. And it's very expensive to get time on a beamline for an experiment, but people do it because it's a good way of getting that resource, that strong light, and you can specify what kind of light you want. If you want infrared, or you want ultraviolet, or you want, I think they can produce gamma, maybe not, but they can just basically say we want this kind of light, and they'll filter out all the kinds that they don't want. So you can get specific lights at very high intensities. That's the gist of a synchrotron. Now, going through step by step how the different parts work, electrons are fired from the electron gun. They receive energy from the electric field in the linear accelerator. I've got a picture of it here. You've got your electron gun, electrons being given off here. There are two plates, a positive and a negative. As we know from looking at electric fields, we know the electrons are going to get pulled towards the positive plate and repelled from the negative plate. So they're going to accelerate as they head towards this positive plate. And we've looked at, back when we did electric fields, how the work done on the electrons as they move through the electric field is work equals the charge of the electron times the voltage between the two plates. The kinetic energy gained by the electrons as they move from here over to here, well, that's your kinetic energy equation, half mv squared. So from this, we can basically figure out that the electrons are gaining this much kinetic energy. They are getting this much energy from the electric field. We can set those two things equal to each other, that the kinetic energy gained by the electrons is just the work done on the electrons by the electric field. Set those two things together, and then we can do a bit of analysis based around that equation. So for example, an electron, it's accelerated to a voltage of 10 kilovolts. What would the electron's speed be after this, assuming that it started from rest? So pulled up the same equation that I had before. Kinetic energy equals the work done by the electric field. We just substitute in our known values, or you can rearrange before you substitute if you want. I could set this v squared equals qv over 0.5 m first if I wanted to. I've just chosen to do it this way. So I've got my mass of an electron, known value, charge of an electron, known value, voltage is in kilovolts, so I have to have that times 10 to the 3 next to that. I do a rearrangement, and then I take the square root, and I get out that the speed of the electron after going through a 10 kilovolt voltage would have to be about 5.9 times 10 to the 7 meters per second. So that's all that analysis involves. You've got your equation. You can either remember it or write down on the formula sheet, or just understand what it means, saying that kinetic energy is equal to the work done. Either way works, but it is this kind of analysis that you're going to need to be able to do. Now, that's happening in the linear accelerator. That's when it's being accelerated after being fired from the electron gun through the LINAC. That's the sort of stuff that's going on. Now, what we're going to do next is we're going to look at the forces in, say, the storage ring, for example, which are due to the forces of magnetic fields, what's going on the electron. So when an electron moves through a magnetic field, the force acting on it causes it to move in a curved path or a circle. I've got this picture down here illustrating how that works. Now, if you remember from some previous lesson, I've got these X's out here. The X's basically signify that the magnetic field is pointing into the page. It says B in, magnetic field is B, is pointing into the page, because we had the notation of crosses mean into the page and dots meant out of the page. There are circles around them which aren't necessary. I think that's just a stylistic choice. I wouldn't put them on there, but whoever made this picture decided to. Normally I just have crosses pointing into the page to show that that's the direction of the magnetic field. So we've got our electron. Let's say it's up here. It's got a velocity tangential, well, just pointing to the right at this point. The force, because it's in circular motion, it's going to be pointing in towards the center of the circle. If we follow the path of the electron, we use our right-hand slap rule to determine the direction of the force on the electron. Velocity, which is our thumb, is pointing to the right. Our fingers are pointing into the page. So the force on a positive charge would be upwards. Because we're dealing with an electron, a negative charge, the force, as you can see, is going to be in the opposite direction. So the force at this point, when the velocity is to the right, the force is going to be downwards. Now, if we follow the electron to a few different points, when we're here, for example, we want our thumb pointing down and our fingers pointing into the page. So I would have my hand in this kind of orientation. The force on the positive charge would be out that way. The force on the negative charge inwards towards the center of a circle. Similar analysis here. Force on the positive charge there, force on the negative charge there. So as the electron moves, there is a force that is basically pushing it in towards the center of this circle. And as a result, that's what the electron does. It moves in a circular path. So at each point along here, you can figure out that the force, force of the magnetic field on the electron is in towards the center of the circle. That makes it a centripetal force, and so we get circular motion as a result. Now, the force of the magnetic field on the charge is F equals QVB. That was our equation for the force of a magnetic field on any charged object of charge Q and magnetic field strength B has to be moving with some velocity V. The equation for the force on something in circular motion, going back to our circular motion stuff from our first area of study, that was F equals mv squared over r. If you remember, the acceleration of something moving in the circle is going to be v squared over r. We take our acceleration, v squared over r, times that by the mass, because force is mass times the acceleration. So our force on something in a circular path can be written as F equals mv squared over r. This is the force on an object moving in a magnetic field. This is the force on an object moving in a circle. These forces in a case like this are going to be the same as each other, so we set this and that equal to each other. QVB equals mv squared over r. We rearrange the equation for r. I know that this v is italic and this one's not, but they're both velocity, they're both the same thing. We rearrange it for r and we get r equals mv over qb. Now, this is one of those equations that you want to make sure you've got on your summary sheet when you go into the exam, because I don't think the formula sheet that you get mentions it. And it's just explain this equation. It's the radius of the circle that the charged object, in this case an electron, is going to move in if you know its mass, its velocity, its charge, and the magnetic field strength. So the radius of the circle, you can calculate it just using this kind of equation. And that's what I'm going to do in my next example. I'm going to say that you've got an electron moving at a speed of 6 times 10 to the 7 meters per second. Just keep in mind, electrons in synchrotrons, they're moving at very high speeds. In fact, this is pretty small by the standards, a pretty small velocity by the standards of electrons in synchrotrons. I think that they're moving quite close to light speed in that case. I'm not sure how close, but it would be, something times 10 to the 8 meters per second, maybe 2 times 10 to the 8, something very large, a very high velocity for these electrons in reality. But it's moving through a magnetic field of strength 1 millitesla. What would the radius of its path be? So it's going to be moving in a circle, just like I said before, because it's an electron moving through a magnetic field. We calculate the radius of its path using the equation I had before. Radius is mass times velocity divided by charge times magnetic field strength. Charge of an electron, what was this? Its velocity that it's moving at, the charge of an electron, mass charge, and then 1 millitesla, milli being times 10 to the negative 3, so 1 times 10 to the negative 3 Tesla. I put in those numbers into a calculator, make sure I've got my brackets where they need to be, and I'm going to get out 0.34 meters, which is not a particularly remarkable number. It's about 34 centimeters path, so you're looking at, how long is 34 centimeters? That large, something like that, a path about that size. And if you think about a synchrotron and the booster rings, they have a much larger radius than that. That's partly because the electrons are moving at a much higher speed than this, so you'd get a bigger numerator. And also I think the magnetic field strength might be less than 1 millitesla, so you get a smaller denominator. So bigger numerator, smaller denominator, you get a larger radius and a bigger circle as a result. So that's all there is to the stuff we're doing on particle accelerators. It's just taking the stuff we've done previously, looking at the effects of electric fields on charges and how they accelerate them, looking at the effects of magnetic fields on charges and how they can be used to force them to move in a circular path, just so that they can be contained in one location, so that they're staying in like a stable orbit, so that they can be pulled and used when they are needed for some kind of experiment. Okay. That's all the stuff on particle accelerators. That's from chapter 3.3 of your textbook, so you should be working through the questions from that, as well as, you're right there, as well as the questions from Ed Rollo on this stuff.